We've been talking about SN1 reactions that proceed without forming carbocations, without forming carbenium ions. And those types of reactions involve some kind of a neighboring nucleophile that can help to push out the leaving group. So you don't form an intermediate carbenium ion. We started off by talking about nitrogen. Nitrogen lone pairs are nucleophilic. They can push out leaving groups even if it means forming a strained three-membered ammonium ring and called an aziridinium ring. And let's go ahead and move a little bit further to sulfur. Oxygen can't do that. The lone pairs of oxygen can't form a strained three-membered ring oxonium ion. But you can do that with sulfur because sulfur lone pairs are in a bigger orbital. That gives them better overlap. And so there's no problem with a sulfur leaning over and ionizing out a chloride in order to generate this strained three-membered ring sulfonium ion. And this strained three-membered ring sulfonium ion has a special name. This is called an episulfonium ion. It's kind of a dumb name, but it's kind of the same name as epoxide. A three-membered ring with sulfur is called an episulfide. But this is a charge on the positive charge on the sulfur. Too many bonds, so we don't call it an episulfide, we call it an episulfonium ion. Boy, that's a mouthful. Now, normally, if you didn't have any other nucleophiles present, the chloride ion would come back in and reopen that ring up. But if you're in the presence of any nucleophiles, including water as a solvent, what will happen is that will open that back up. And then eventually you'll end up generating HCl in that process. So this is particularly bad if you're getting this mustard agent. This is called a sulfur mustard. On your skin, inside of your lungs, in your eyes, it creates hydrochloric acid, it alkylates proteins, it reacts with water, does everything. But of course, having hydrochloric acid in your eyes and in your lungs causes serious problems. You can have substitution on these systems. So if you look down here, you can imagine if we've got a substituent on there, you can still bend over and push out other good leaving groups. Tosylate, mesylate, chloride, bromide. And if we don't have this in a whole sea of water and we include a good nucleophile, well, we can attack that episulfonium ion with a different type of nucleophile. So here's an example where if you include ammonia, that ammonia can open up that episulfonium ion. Let me go ahead and reverse the way that I've oriented that ring there. And so you end up with this episulfonium ion. And if you have ammonia in there, the ammonia is a good nucleophile that can attack. And that can open up the ring. Now, we've talked before about three-membered ring onium ions. Protonated epoxides, aziridinium ions. These prefer to open at the more substituted site. So you can get a ring opening, this SN2 type ring opening, either at the more substituted or the less substituted site. And the preferred site in these cases, as you can see here, you get a 4-to-1 mixture favoring opening at the more hindered site. That's not unusual. You can even attack at tertiary centers, which is very hard to do if you're doing simple SN1 reactions, but it's a special property of these three-membered ring onium ions. So you do get some attack at the primary position, the less hindered position, but that's the minor product in this case. Let's take a look at another example where you get SN1 kinetics, but without forming a carbocation intermediate. And so here's an example where there's two different diastereomers of an acetoxy tosylate. And what's interesting about this case here is that if you look at the relative rates at which these two species undergo substitution reactions, this cis isomer that I've drawn over here reacts more slowly than the trans isomer. It's a factor of about 100, so the trans isomer is 600 times more reactive to undergo substitution with sodium acetate, with an acetate nucleophile. And let's try to understand why that should be true. To help us understand that, we're going to have to draw out this acetate group. Let me go ahead and I expect you to know the chemical structure of an acetyl group or acetate or an acetate ester. Sodium acetate you could draw looking like this if you're drawing a charge-separated structure. That's the nucleophile in this reaction. Let's go ahead and try to draw out this trans substituted, this trans isomer. this acetoxy tosylate. And I'm going to do it using a chair. That'll help us to understand the relative orientation of these groups. When I draw chairs, the most important, if you want to draw a good chair, the most important thing you can do is get those first two bonds right. And when I do that, I'm being ultra careful never ever to overlap these two carbons vertically, because when I draw axial substituents, I do not want those substituents, those bonds, right on top of each other. If you misdraw this so that these two axial bonds end up on top of each other, you'll never be able to finish a chair. So it's critical that you get these first two bonds correct. And after you've done that, everything else is kind of easy. I draw two lines that are parallel and of equal size, equal length, and now I can just finish that chair up. So now I want to draw the tosylate group going up. I'll put that over here. That's going to be straight axial. I'm also going to draw the acetoxy group axial, but it will be going straight down. It's anti to the tosylate. Now this is not the only conformation of this molecule. There's another chair-flipped conformation where they're both equatorial, but that's not the reactive conformation. So I'm drawing the less stable conformation, but it's the reactive conformation. And I'm going to draw out that acetate ester so you can see that there is a carbonyl group here that is 5 atoms away from that tosylate. Boy, that's a great ring size. So if we can use this carbonyl lone pair to attack, we end up doing that through a very favorable 5-membered ring transition state. And let's go ahead and draw the structure of that intermediate that we generate in that process. So we'll end up generating an intermediate, and I don't really need to draw a chair conformation anymore. I just want to emphasize that now I've got this 5-membered ring that looks like this, and it's easier for us to open that ring up. Let me draw that other bond going downward. Now, I think it's kind of obvious that I can open up this redo an SN2 reaction with my acetate nucleophile. So here's my acetate nucleophile, and if I open that up to an SN2 type substitution process, I'll get inversion of configuration, and that explains this product that you get over here. But what's interesting about this is that you also get the other enantiomer of this product where this acetoxy group is going up. So that can't be the same acetate that was originally there. The way you explain that is you simply draw an opening on the bottom side of this flat structure. Let me redraw this other alternative reaction outcome, this other reaction pathway. I'll draw exactly the same molecule, and I'll have my acetate add on that bottom carbon. Now notice when I push the arrows, I can still make an ester leaving group. I'll just push the arrows from here when I break the bond and give the electron to that oxonium O+. So you get a mixture of two different enantiomers in equal amounts because it's equally probable that the acetate could have added from at the top carbon or added at this bottom carbon. You could have drawn a different resonance structure for that 5-membered ringonium species. Would have been the same deal. Okay, so esters, when you have an ester like this one right here, or an amide, if you have an amide nitrogen, the lone pairs on that carbonyl can participate in neighboring group, as a neighboring group, leading to SN1 type kinetics, but without forming a carbocation intermediate. You're pushing out the leaving group in this case. Oxygen lone pairs are not that nucleophilic, but when you're 5 atoms away, that makes that process favorable. Okay, let's take a look at another less obvious example of neighboring group participation, SN1 type substitution that doesn't involve a traditional carbocation, traditional carbenium ion. So I've got two different norbornyl ring systems, and it's a little bit difficult to see here, but there's a double bond right here. And this double bond there, that double bond, I'll just write double bond, makes all the difference. Look at the difference in rates for SN1 reactions in this case. Two different secondary tosylates. Secondary carbocations are not really stable. There's nothing special about this carbocation here. It's not like a 2-norbornyl carbocation. It's not, doesn't have the same kind of special alignment. But when you have a double bond out here, it has a pretty dramatic effect. And you can see here from my arrow pushing that what's happening here is that there's a sigma star orbital for this tosylate bond that's sticking on the back end. It just sticks out the back end of that carbon tosylate bond. And that pi system, the pi electrons in that double bond are above and below the plane of that pi ring. The pi electrons in that double bond are overlapping in space with the antibonding orbital of the tosylate 100% of the time. And you can't stop that from pushing out the leaving group when you're doing a substitution reaction. So if you follow the arrow pushing, let me go ahead and draw out the carbocation that my arrow pushing would generate. Now you can't tell which carbon my arrow pushing is going to form a bond to. When I attack that tosylate carbon, you can't tell. You'll have to wait until I draw my next structure. And so let me go ahead and try to redraw that Norbornal ring system. I'll try to do it in a way where I can make it easier to see where I'm forming that bond. Let me draw this other bond behind. And I'm going to draw a bond to that back carbon. And the tosylate is over here at his left. And that leaves a carbenium ion right here. Wow, that's a pretty good carbocation. Look at that. It's a cyclopropyl carbonyl cation, so the strained bonds in this three-membered ring are helping to stabilize that, but it's also a 2-norbornyl cation. So it has a lot going for it here. So it's not obvious that you would have gotten such a carbenium ion with so many stabilizing features. Now, you can get this type of neighboring group participation even in cases where the conformation isn't great all the time. I'll show you another example down below where what happens if your structure isn't locked into a reactive conformation. So I've got an example down here where this tosylate is very far from that double bond. And with that double bond, if you have the double bond there, it's faster, but not as fast as up above where this is 100 billion times faster than without the double bond. Down below here, that double bond only makes it 95 times faster. 100 times faster, nothing like 100 million, but still faster. And so how do we explain the fact that it's faster but not a lot faster? Well, this bottom molecule here can spend some time in its chair-flipped conformation. So let me go ahead and draw the chair-flipped 5-membered ring, like this. There's my pi bond. And if I chair-flip that, there's an H on the bottom here. If I chair-flip that, this alkyl group with the tosylate can spend some of its time, a little bit of its time in this conformation. Not a lot of time in that conformation. That is not a favorable conformation. By far, the preferred conformation is this other conformation on the left. But for the small amount of time that it spends in this conformation, these pi electrons can help push out that tosylate leaving group. So this is why it isn't as good as the case up above, which is locked into a reactive conformation. This case down below spends only a small fraction of its time in the reactive conformation. But when it does this, you'll end up forming a carbenium ion by using that pi bond. You can form a carbenium ion. And I don't know if this was obvious to you, but look at this carbenium ion. That's a 2-norbornyl cation. I'm not sure if you recognize that, but it's our old friend, the 2-norbornyl carbenium ion. And we've seen those before. You know, the bonds in 2-norbornyl cations are aligned, well aligned. A little extra p character because the bonds are, it's not like normal 109-degree bond angles. So this, you know, when you're not locked into a reactive conformation, it's only a minor amount of some conformational isomer that will be participating in the reaction. So it's not 100 billion times faster, it's only 100 times faster. Okay, so the pi bonds don't have to be right next door in order to help push out leaving groups like an allylic cation and a allylic carbenium ion. Okay, let's take our last example of neighboring group participation where you do SN1 type reactions that don't go through traditional carbocation type intermediates. Okay, here's an example. I'm showing you it's a pretty subtle effect here that they're doing a substitution reaction using formate instead of acetate. So they're using formic acid as their nucleophile. Here's the chemical structure of formic acid. Why would somebody use formic acid? Not sure what I just did there on the screen. Let me try to erase that. There we go. why would somebody use formic acid? I would expect that to be a little bit more polar than acetic acid, so maybe you want to stabilize carbenium ions a little bit more, carbocations, stabilize charge separation. But the lone pairs on this carbonyl are the nucleophile, and they can substitute. So you can see in the products here that they've substituted the tosylate leaving group with as a formate ester. But you get a different outcome depending on whether, or a different mechanism, depending on whether you have a nitro substituent at the para position or a methoxy substituent at the para position. And you wouldn't know that there's any difference in the mechanism, but some clever person put a C13 label right next to the tosylate group. And if you have a nitro group at this para position, it doesn't make any difference. That C13 label ends up right where it was in the starting material. But if you have a methoxy group here, 50% of your C13 label ends up next to the nucleophile. The other 50% ends up next to the benzene ring. Now, how do you explain the fact that suddenly 50% of your C13 label is over here next to the benzene ring? Let's go ahead and talk about the mechanism that will explain that. And that is to use neighboring pi bonds. So the neighboring pi bonds in this benzene ring, this is an electron-rich benzene ring when you've got a methoxy group that has lone pairs on there. And those pi electrons in that benzene ring can help push out the leaving group. If the benzene ring has enough electron richness, is nucleophilic enough, then the pi bonds of the benzene ring can help to push out the leaving group. And you'll generate this ring that looks kind of crazy and unstable. You've lost aromaticity. That's not so good. You've generated a carbenium ion. That's not so good. But let's look at this carbenium ion. That's a cyclopropyl carbinyl cation. And you can draw another resonance structure where you delocalize this carbenium center on the other side, and it's still a cyclopropyl carbenium ion. We call this particular carbenium ion, with that three-membered ring on a dearomatized arene ring, we call that a phenonium ion intermediate. It's a phenonium ion, and it's an intermediate when you have electron-rich aromatic ring systems. They can participate in that way. Now, you could just as easily, as I've indicated below here, you could just as easily have drawn that same mechanism by starting with the oxygen lone pair. I've told you before, most mechanisms arrow pushing mechanisms start with a lone pair. So you wouldn't have been wrong if you started with the lone pair and did it like this. It's the equivalent mechanism. So if I push these electrons all the way here, it would look like that. It doesn't follow the three arrow rule, but there's nothing wrong. And once you get out of this class, you can break the three arrow rule. But the reason why that benzene ring is so reactive is because of that oxygen lone pair. Makes a resonance structure of my first phenonium. These are the same mechanism. And how do I know it's the same mechanism? Because this is a resonance structure of that, and that means these are the same. Just because I generated a resonance structure doesn't make it a different mechanism. Now, if you've got a nucleophile nearby, that nucleophile can reopen that ring. It wants to regenerate aromaticity. So if I push the arrows like this, then I can just regenerate aromaticity, and that leads to substitution. And because you can attack either side, right, you could have just as, I'll use the bottom structure here so I don't have too many arrows. I could just as easily have attacked the bottom carbon atom. There's no difference in reactivity there. Right? So you could attack the top carbon of that cyclopropane ring or the bottom carbon, and that's why that label, that C13 label, gets scrambled between those two positions. Right? If the C13 label was up here, you would have very little difference in reactivity. Right? Half the time you'd add to the C13 carbon, the other half the time you'd add to the regular isotope 12 carbon. These may seem like exotic intermediates, but there are anti-cancer drugs that are based on these kinds of mechanisms produced by nature. Nature is very clever at using things like cyclopropyl carbinyl cations, aziridinium ring opening, and neighboring group participation as a selective way to position electrophiles near DNA. So it's commonly used in nature. We're going to have a major kind of a major change here to a new topic, and it's a topic of migratory displacements. So these are going to involve some kind of an ionization reaction, but what's interesting about these is that we're going to use sigma bonds, generally sigma bonds to carbon, in order to push out leaving groups. So if I position very carefully an alkyl group, a CC bond next to a great leaving group, that CC bond in some cases can help push out that leaving group. We've been seeing cases that are starting to look like this in the problem sets that you could have interpreted in this way. Now, carbon-carbon bonds are not very nucleophilic. So you really need to have rigged systems here where the bond can be absolutely aligned with the antibonding orbital of the leaving group. And we're going to need to do something to weaken that bond and make it more nucleophilic. That's our whole trick, having a trick that weakens this bond and makes it more nucleophilic so a carbon-carbon bond can be reactive enough to push out that leaving group in order to migrate the R to where the leaving group was. Let's go and take a look at some examples of this. And the canonical example in this class of reactions, migratory displacements, would be the Pinacol reaction. So we're going to refer to this as the Pinacol rearrangement. And it's named because the starting material for a classical canonical Pinacol rearrangement is this 1,2 diol with 4 methyl groups on there. That's called Pinacol. We're not going to talk about the mechanism for synthesizing that from acetone. It's a simple reaction involving cheap materials to make that. So it's readily available. Pinacol is readily available. And when you treat Pinacol with sulfuric acid, that seems to be what everybody did 100 years ago, is they took everything and dumped acid in it to see what would happen. You get a rearranged carbon structure. You get a quaternary center with 3 methyl groups on 1 carbon atom and a carbonyl group. So the structure has changed, and we call this ketone pinacolone. It's the ketone derived from Pinacol. And so let's go ahead and see what's happening in this reaction. So I've drawn the starting material of a 1,2 diol, of a vicinal diol down below here. So you can see there's a 1,2 diol in this structure. And instead of having 4 methyl groups, I've got some different groups here, H's, phenyls, and methyls on there. And I've drawn this in a very particular way so that you can see the importance of bond alignment and a very particular arrangement. So I think you can guess what's going to happen in the first step of this reaction since you've got sulfuric acid in there. We're going to start off by protonating the alcohol. We're going to protonate that alcohol group with the sulfuric acid or with some sort of acidic species that's in that solution. Now when I draw this intermediate, I'm going to be very careful to preserve my well-thought conformation that I've drawn for the starting material. And the arrangement that I'm being super careful to make sure is evident here is this arrangement right there, where I can see that the group that migrates over, here's the group that migrates over. So I start with 1 phenyl group on this carbon, and I end up with 2 phenyl groups there. One of these phenyl groups is shifted over. And I'm going to be super careful so that you can see that that original phenyl group is exactly parallel to the leaving group. And not just parallel, but anti and parallel. And we refer to that rearrangement as anti-periplanar. When one bond is parallel to another bond, but they're sticking in opposite directions. They're pointed in opposite directions. Recognizing anti-periplanar relationships is one of the most important skills in organic chemistry. It's why you have to be good at drawing chair conformations. And if you can't recognize anti-periplanar relationships, most of organic chemistry will be a mystery to you. So let's go ahead and finish drawing out this protonated alcohol here. That's the leaving group. And I'm going to draw my other substituents. I'm going to draw 2 bonds here. And I'm going to make sure that parallel to this bond, but anti-periplanar to it, is another bond on that other carbon. And then parallel to this bond right here, I'm going to have another bond over here. So let me just do that in black. I don't need to see red bonds for those. But I'm drawing this conformation so that you can see the anti-periplanar relationships between all the bonds. And when I draw it in this conformation, it sets me up to fuse this onto chair rings, right? A well-drawn chair will match exactly on this structure, right? This is exactly why we draw chairs, is so you can see those critical anti-periplanar relationships. So I've got this water leaving group, but this bond here, this phenyl carbon bond, is not nucleophilic enough to push out that leaving group. It's still not nucleophilic enough. And that's why this other oxygen atom is critical. This other oxygen atom has lone pairs. And those lone pairs can be anti to this phenyl carbon bond, and they can help break that bond. But the phenyl doesn't walk away as a phenyl anion. The oxygen lone pair is simply weakening this phenyl carbon bond, lengthening that carbon-carbon bond. You could see that in a crystal structure. You would see that the carbon-phenyl bond is a little bit longer than a regular one. And that allows this phenyl carbon bond to act as a nucleophile and migrate over. Kind of like a 1-2 shift, but you're not shifting to a carbocation. And this is called a Pinacol rearrangement. It's driven by this oxygen lone pair here, which is weakening this bond and making that bond more nucleophilic and better able to migrate over in a 1-2 shift that pushes out that water-leaving group. So we don't generate a carbocation intermediate in this reaction. You would have made a lot of sense if you said, oh, I think I'm going to generate a carbocation intermediate. Somebody has to do mechanistic studies in order to show that there are no free carbocations, no free carbenium ions with only 6 electrons in this reaction mechanism. And we've had problems on our problem sets that we interpreted in this way, but now that you know about the Pinacol reaction, we would expect you to look for these 1,2 diols and draw out Pinacol type mechanisms without forming carbenium ions. Let me go ahead and draw out this next intermediate here. Next intermediate has that carbonyl group. In this case, it's an aldehyde. Now both the phenyl groups are attached onto the same carbon. So one of these 2 phenyl groups is migrated over. I'll just darken it. There's, I'm not trying to apply stereochemistry, but there's 2 phenyl carbon bonds. And this is still protonated on that oxygen. We'll need to remove that proton from that oxonium group. I'll just draw an A- here to do that, like this, and then we can pull the proton off. There we go. That's not it's a crazy looking arrow there. Whoops, I didn't mean to erase so much of that. Well, I'm not quite sure how to wedge in there. That error is going to have to do for us. Okay, not all groups are equally good at migrating. Some groups are better at migrating over and pushing out water molecules in the Pinacol reaction. Somebody has taken the time to study this. The groups that are slowest to migrate, notice that there were, oops, I forgot to put the H atom here. Notice that there was an H atom there. Alkyl groups are the worst. Primary alkyl groups are the worst at migrating. And if you had a T-butyl group out here, the T-butyl group would be better at migrating than if this was a methyl. T-butyl would be better at migrating than an ethyl group. T-butyl would be better at migrating than an isopropyl group. The better you are at, the more substituted things that can stabilize carbenium ions more tend to be faster at migrating. Vinyl groups, double bonds, can migrate over. Right? If you had a double bond here, that would migrate faster than any of the alkyl groups. And finally, if you had a phenyl group like this, it migrates faster. And maybe that's a little bit easy to understand if we recognize that there's pi electrons in this benzene ring that can help participate to some extent during that migration, almost like that phenonium type situation. Okay, so that's the migrating group ability. It's not equal. Not all groups migrate equally well. During the lecture, I'm re-recording this lecture, somebody asks, well, how do you know which OH is going to be protonated? There's no selectivity in the protonation of the H. You protonate this OH, and then you take the proton off. You protonate the other OH, and then you take the proton off. You protonate this OH, you take the proton off. Proton transfers are fast, reversible. They're happening zillions of times a second. What matters is the rate of the migration to form the CC bond. That's what's really dictating the selectivity here, not which OH protonates the fastest. That has no impact on the which group migrates. Okay, let's look at a related reaction that involves a better leaving group than water. What's a better leaving group than water? Well, in this case, nitrogen gas. When we teach introductory organic chemistry here at UC Irvine, we teach the synthesis of arene diazonium reagents using a species called nitrous acid. You can't buy nitrous acid. You make that using sodium nitrite. It's a salt, and then you add HCl or some other acid to sodium nitrite to generate nitrous acid in situ. Nitrous acid isn't stable. But if you generate nitrous acid in the presence of amines, nitrous acid will diazotize. We call this diazotization of an amine. It converts amines into diazonium groups, and diazonium is N2 gas. It's ready to act as a leaving group. Let's go ahead and draw out that transformation. I'll go ahead and draw out the formation of this. I'm just going to draw the diazonium group. I'm not going to go through the mechanism. It's quite a long mechanism to. It's quite a long mechanism to draw out this formation of the diazonium group. It's not really what the main subject of what we're talking about. So let me go ahead and start off by drawing the chair. I think that'll be the most helpful. The chair is not really important for this reaction mechanism. I just want to be able to draw out some sort of an anti-paraplanar relationship to this leaving group. I've got this stray dot on there. Maybe I can use that for my. That's not good. Let me. I'll just erase that dot somehow. There we go. So you've got this diazonium leaving group, and you'll notice that in this reaction, this carbon-carbon bond has migrated over somehow. The carbon-carbon bond that used to be over here has migrated over and is now attached to this carbon. So we started with a 6-membered ring here, and now we ended up with a 7-membered ring. And what has happened in this reaction is that one of these bonds has moved away from this carbon and is now attached to the CH2 that used to have the nitrogen gas. But this is just like the Pinacol reaction. It's like that CC bond is not very nucleophilic. The migration of that bond is accelerated because there's a lone pair that's donating downward and weakening that bond. So let's go ahead and draw that lone pair donation here. Right? There's a lone pair that can weaken this CC bond. Let me draw it in blue so it doesn't interfere. There's that CC bond, and it can help push out the N2 that is anti-paraplanar to that CC bond. So in a different conformation, I could have used this back bond here if I had drawn the diazonium leaving group anti to this back bond, but I didn't do that. So ultimately, this will after that rearrangement would give you this protonated oxonium, and then you would simply remove a proton from that group just through a proton transfer step. You can't buy nitrous acid. It's not stable, so you can't put it in a bottle. You have to make it yourself. Typically, you use sodium nitrite and hydrochloric acid. In this case, they're using sodium nitrite, just a white powder salt, and sulfuric acid. And so in this case down below, you'd look at this and you might think I'm trying to do one of these Norbornal things to you or use the oxygen lone pair. That's not what this problem is about. This is just about diazotization. Let me go ahead and draw out the intermediate here. Let me go ahead and draw out the intermediate is a Norbornal ring system, but it's not going through a Norbornal cation. We don't need to invoke any of that. This is a Tiffano-Demjanov reaction, very much like the Pinacol reaction. And it's doing a ring expansion here. So again, we're forming a diazonium group. Again, there's many steps in that mechanism. You should have covered this in a sophomore organic chemistry class. All books, even the web, will have mechanisms for diazotization. Again, let me write that down in case you. This process is called diazotization, turning an amino group into a diazonium leaving group. Diazotization. And again, we've got this arrangement where there's lone pairs on this oxygen atom that are weakening this bond. And then that carbon-carbon bond is now more nucleophilic, weaker, more nucleophilic. Whew. It's crazy. I'm wearing this little glove that's supposed to stop my finger from doing weird things and my palm from doing weird things on the iPad, and it's still not totally working. Shows how clumsy I am at using an iPad to draw. Okay, so you form, I won't show all the steps. There's lots of steps for forming the diazonium. And then you end up with that ring expanded product, and there's another proton transfer at the end. Okay, so you make a good leaving group, right? It doesn't get much better than nitrogen gas, and you can push out that leaving group using a CC bond. That's pretty amazing. A weakened CC bond that's weakened by a neighboring lone pair. Let's go ahead and move away from these from the all-carbon type system, or what seems like the all-carbon type system, and look at a not obviously related reaction called the Baeyer-Villiger reaction, sometimes referred to as a Baeyer-Villiger oxidation. And it's traditionally used for ring expansions. You could do it in acyclic molecules, that's not as common. And you can see what's happening here is you take a ketone, usually a ketone, in theory you could do it with aldehydes, but it's not really common. And you treat that with a peroxy compound, oxygen-oxygen bonds in a peroxy compound. Let's look at this. There's an oxygen-oxygen bond. Somewhere in that reaction, the oxygen-oxygen bond is going to break. Oxygen-oxygen bonds are weak, right? They want to break, they want to cleave. It's easier to do SN2 type processes on oxygen-oxygen bonds. So you can see what you've done at the end of the reaction, that there's many steps in this process, is that you've inserted that oxygen between one of these two carbon-carbon bonds. And the major product in this reaction is the one where you substitute in between the more you put the oxygen in between the more substituted carbons. So if I look at these two bonds here, here's a bond and here's a bond. The one that has more alkyl groups is the one that's favored in terms of substitution. So you'd get what, an 87% yield, and the other product was isolated and only 5% yield. So and that's the general regiochemistry. You substitute and the more you put the oxygen atom, insert it into the carbon bond that's more substituted. Let's take a look at the mechanism for this. It's most common. You could do this using hydrogen peroxide and adding acid to the reaction, but usually people just use peroxy acids. Like MCPBA is a very common peroxy acid that you should have learned about in a sophomore organic chemistry course. MCPBA is usually used to make epoxides out of CC double bonds, but in this case, it's being used for a different type of process. The mechanism for the reaction starts off with proton transfer. We're going to activate, it's kind of like forming an acetal is the first step for this reaction. So we'll come over here and we'll take a proton off of this peroxy acid. And that's going to generate two key reactive species when I do that. One of these is going to be this protonated carbonyl. Very easy to add to a protonated carbonyl. Even an oxygen nucleophile can add to a protonated carbonyl. When I do this, not only does it generate a more reactive carbonyl, but it makes this peroxy acid more reactive as an oxygen nucleophile. And so now it's a peroxy, I'm not sure I would call it a peroxy carboxylate. There's an anionic charge there. And so that makes it very easy for this lone pair to add in to that protonated carbonyl. And we're going to form kind of the equivalent of a hemiacetal here. Let me circle this charge because it looks like a bond. Yeah, that's a negative charge, just so that's clear. And so we're going to generate this intermediate. Boy, I've really messed up that. Just trying to circle that negative charge so you can tell it's not a bond. So we're going to generate this intermediate that is now almost ready for our key rearrangement. I'm going to draw this OH bond because I need that in the next step. So that lone pair, that oxygen lone pair, is 7 atoms away from that proton. Now, I've told you before, don't draw proton transfers via 4-member transition states. I've said that you can't reach a good trajectory, but 7 you can do. 6 is awesome. 5 is great. 7 even, proton transfer is reasonable. It's quite plausible. And so we're going to draw this next intermediate that is a Switter ion. It's got 2 charges somewhere in the structure. Not necessarily next to each other, but I'll circle the charge so it doesn't look like a methyl. Look at that weak, weak bond. That weak, weak oxygen bond right there. I'm going to cleave that oxygen-oxygen bond, and I'm going to use a CC bond to cleave it. So before, I was using a CC bond to attack a carbon atom, and in this Baeyer-Villiger reaction, I'm going to use one of these 2 bonds right here. It doesn't matter which one I use, they're symmetrical. I'm going to use one of these two bonds to migrate over and cleave and push out that oxygen leaving group. The leaving group isn't that great, but the bond is weak. There we go. We're going to push that. But why does that CC bond, why is that CC bond able to migrate over and push out that leaving group? The reason it can do that is because the lone pairs over here on this O- next door are donating in and weakening that bond like that. And that directly gives you this structure over here, plus a carboxylate anion leaving group. Let me go ahead and draw the leaving group. It's not really interesting for the reaction, but this is the byproduct of that process, is that this has now acted as a leaving group. So you start with a four-membered ring. You can see you start with a four-membered ring, but when we migrate this bond over here, that makes a five-membered ring. That's going to be a five-membered ring right there, with a carbonyl sticking off the, with a carbonyl sticking off the edge. Okay, that's a Baeyer-Villiger reaction. It involves a migration of a CC bond, to cleave an OO bond, a weak OO bond. We're attacking oxygen, and we're cleaving a weak OO bond. All right, let's go a little bit further here and draw a similar reaction. That involves electrons weakening a bond and then having a leaving group leave. So this is called a Wolff rearrangement. I can, in order to understand a Wolff rearrangement, I have to redraw this structure in an alternative resonance form. So this is the most common way to draw a diazo functional group. But it really belies the structure of this reaction. There is nitrogen gas built into this structure. And so let's draw a resonance structure that makes it a little easier for us to see that there's nitrogen gas in here. I'm going to start off by drawing a resonance structure that helps me to see that there's N2 ready to act as a leaving group under the right conditions. Oh, I've got that. Gee, I'm drawing the wrong thing there. Okay, let me start off by drawing the resonance structure that helps us to see that there's nitrogen gas built into this molecule. So I'm using the lone pairs on that N-, and I'm going to draw a resonance structure now that looks like an enolate. Wow, and it's like an enolate, but it's also like a diazonium. Well, it is a diazonium. Look at that nitrogen gas ready. If we could just find a way to help that leave. Let me circle that so it's obvious there's a charge here because I'm circling the charges. That's the best way to think about this diazocarbonyl compound. Diazocarbonyls are stable. You can isolate them and crystallize them and chromatograph them, but it's surprising that it's stable enough to work with when it's got nitrogen gas ready to act as a leaving group. And if you heat this system, you'll find that there's a migration that occurs. I start off with an R group over here on this carbon, on the carbonyl carbon, but now that R group is going to end up attached over here. Right, the methyl group and the R group are going to end up attached on the same carbon. There's been a migration that has occurred here. And let's go ahead and try to piece together that process. I'll draw the arrow pushing here. So there's a lone pair here. Let me draw it really big. It's kind of too close to that negative charge. That lone pair is donating in, is attacking this CC bond, and it's weakening this CC bond right here. That bond right there is weakened by that O- lone pair. And that bond is weakened, it's longer, and it's weak enough and long enough, if you heat this compound, if you heat it, that bond will migrate over and push out this diazonium leaving group. And it will generate this kind of strained looking, weird looking species called a ketene. Ketenes are reactive. So if you heat these things, they can do this rearrangement, and this is called a Wolff rearrangement. This reaction of diazoketones that causes an R group to migrate and push out nitrogen gas as a leaving group. This process is widely used, or has been widely used in the manufacturing of silicon chips for computers. There's a photochemical version of this where instead of heating things, you shine light on them. And there's a particular type of species that's an industrial reagent, diazonaphthoquinones, where you've got a benzene ring here, helps it to be good at absorbing light. And so instead of heating this, if you shine light on it, I'll draw that same resonance structure. Whoop. Let me go ahead and draw that preferred resonance structure for the Wolf rearrangement, where I can see that nitrogen gas as a potential leaving group here. There we go. I'll just put X here for that sulfonate anion. And so when you shine light on this species, right, if you shine light on this, it can drive that Wolf rearrangement. It's kind of the same way that heating would drive it. And so if I draw those lone pairs over here, I can push down those lone pairs. When you hit this with a photon of light, it absorbs the photon and it activates this process to occur. And this is the way they make those patterns, or one of the reagents they use to make patterns on silicon chips. You put this goopy liquid on here that contains this Novolac resin, and then you shine patterns of light through this clear mask that has these patterns on there, and wherever the light hits, it creates these ketenes. And then when you add base, aqueous base to this, the hydroxide can then attack the carbonyls and then convert those to water-soluble carboxylate anions. It just washes away and leaves behind these patterns that they can use to then etch and convert into silicon dioxide or some other process that. So you can see at the end, I'm not going to draw all the intermediates in this ketene hydrolysis, but you can see that you've added, when you add to that ketene, you're eventually going to pick up a proton here. There's some extra proton transfers I'm not drawing. Ketenes are reactive. They'll react with amines. They'll react with hydroxide. A very common reactive species. And we'll see some similar cumulines reacting shortly. All right, so we've been talking about migratory displacements, where carbon-carbon bonds can shift over and push out leaving groups, which is quite extraordinary, but you have to weaken those carbon-carbon bonds.